Tá. Richard, quando você falar, a gente começa. Será que...
Tá com eco?
É, com barulho. E tá com eco também. Tá com ruído, não sei. Parece interferência.
Pode ser alguém que esteja na sala, não é.
Porque o seu aqui também tá dando pra ouvir a sua voz pra... Será que é?
Então, esse aqui não é.
Tá fazendo barulho.
Tá fazendo barulho?
Sim.
Então, eu vou mudar o. Só um momentinho.
Não, mas pode ter relação, porque eu cheguei perto aqui.
Eu vou ver a parte do microfone, só um momento.
Pode ser isso, né?
Será que era o computador da Isabela? Estava com... Não era isso, não?
Tem um microfone que é abertinho, que dá pra dando pra ouvir.
Mas agora parou, né?
Pode ser o webcam, que não é? Teste. Nossa, tá dando pra eu ver. Eu acho que é essa. Testando. Será que eu tô com o microfone comigo? É isso aqui mesmo. Deixa eu montar ela. Câmera.
Ok. Já estamos no ar igual, né? Não. Alô? Não sei se está funcionando, na verdade.
Parece que não, né? Alô?
O seu sim, mas este está funcionando? Não, não está funcionando. Ah, sim está, mas está muito baixo, né? Agora sim? Não. Não, não sei. A gente grita e já. Não, mas não, se não falo para aqui, já acabou, já. Alô? Agora sim. Vamos lá, mas não sei se está... O quê? Tem alguma coisa que... Sim, mas não sei se é o microfone.
Tem uns aqui, deixa eu ver como é que tá isso. Alô, testando. Ué. Eu vou pegar outro microfone. Tem um aqui, ó. Desculpa pelo problema técnico.
Não, que isso? Tá aqui.
Alô, teste. Eu não tô me ouvindo. Alô? Testando. 2, teste. 2, teste. 2, testando. Teste. 2. Testando. 2, teste. Alô, teste. 2, testando. Alô, teste. Alô, testando. Fala o seu também.
Alô?
O seu tá ok, né?
Sim, aí
Vamos ver se
já
vai.
está.
Deixa eu achar.
Eu achava que era seu, mas não acho.
É, eu tirei o microfone e a caixa de som.
Então não é.
Acho que
Não, porque você ficou perto e depois não passou nada. Não aconteceu nada. Não. pessoal está vendo. Aí sim, agora sim. Agora está funcionando. Está funcionando.
Vocês estão me ouvindo? Alô?
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 Tudo funciona, né? Estamos aqui funcionando. Então, já estamos transmitindo, né? Okay. Welcome to another seminar. We are really sorry about this delay. We were having some troubles with the sound, but now everything seems to work perfectly. And today we are very glad to having with us Isabela Matos. Many thanks for being here today, presenting your work. And let me just very briefly introduce Isabela. She graduated in physics in the Federal University of Rio de Janeiro, where she also made her PhD with a sandwich stay at the University of Geneva in Switzerland. And currently, Isabela is a postdoc researcher at the ICTP and UNESP. Her research focuses in the use of gravitational waves to study cosmological models. And this is precisely the title of her talk, Cosmology with Gravitational Waves. And as always, if you have a question in the Google Meet, well, the question will be asked after the presentation. If you are in the Google Meet, you can raise your hand and ask your question. And if you are in the YouTube, you can write your chat down, your question in the chat, and we will ask the question for you. So whenever you're ready, Isabela, you can start.
So thanks a lot for the invitation. It's very nice to be here. Well, I will discuss today about methods to do cosmology with gravitational waves. I hope this can be interesting for you. And please stop me at any moment if you have questions. So I first discuss a bit about what is cosmology about, as a reminder, what is the standard model and some of its modifications. And then we discuss a bit about gravitational waves, and then we enter the main theme, which are which kinds of methods we can use to learn more about the history of the universe in the large scales using gravitational waves in different kinds of gravitational wave events. Okay, so yes. So first of all, cosmology is about the history of the universe in the larger scales. So it's about trying to understand how the universe came from something that was hot, dense, pretty much homogeneous, not very funny, and went through several physical processes until it had structure, so complex structure in the large scales with galaxies and clusters of galaxies. So the standard model of cosmology is the so-called lambda CDM model, which stands for lambda, the cosmological constant, plus cold dark matter. And this model tells us that today the universe is mostly made of things that we don't know, which are dark matter and dark energy. So dark matter is this excess of matter that we observe. Is this excess of matter that we observe in the large scale structure of the universe, and dark energy is this component responsible for the accelerated expansion that we see in the universe today. Okay. The lambda CDM model is a 6-parameter model based in general relativity as the theory of gravity. And but because of these big unknowns of dark energy and dark matter, there were several modifications of the lambda CDM model that have been that were proposed in the last decades that try to explain these components, especially dark energy. But the lambda CDM model was very successful until, let's say, 10 years ago. It was being able to predict what we observe, several different kinds of observations for cosmology. So I try to list a few of them here. So for example, very importantly, we see the galaxy distribution in the sky. We see the redshifts of the galaxies, also the shapes of galaxies. And with this distribution, you can constrain very much this model. A second very important probe is the cosmic microwave background. So these first lights that we can see in the universe, the oldest light that we can see in the universe, whose anisotropies are also very powerful to constrain the parameters of the model. But for us today, the most important probes of cosmology will be these objects that have some universal property. So that have some properties that that can be standardized, such as the standard rulers, candles, and the standard sirens, which are the gravitational waves. So for example, we have the pulsars, which have a period of rotation that is very irregular. You have also the supernovae that are very important because the peak of their intensity is directly related to the distance to the supernovae. Okay, and measuring distances in a curved spacetime is not a trivial thing, right? For example, with the supernovae, the distance you can measure is called the luminosity distance, whose relation to the redshift of the same source depends of the history of the expansion of the universe from the supernova to us. So it tracks how much the universe expanded from the supernova to us. And this expansion, of course, is this function here, h, the Hubble parameter. It depends on several things. So the current rate of expansion of the universe, also the amount of matter in the universe, the amount of dark energy, and so on. Okay. And yeah. And this distance will also appear in the standard sirens. That's why I'm talking about this. So all of these different cosmological observations, they were quite successful, as I was saying, until 10 years ago. And they were like quite compatible and allowed us to measure these several parameters of the model. And that's why the lambda CDM model was also called the concordance model. However, these more theoretical problems, if you want, of not having a fundamental theory that describes dark energy, not having very good explanations for what is dark matter, continue to motivate alternative models. More recently, there was another problem that we have, that are the tensions, notably the Hubble tension. So different measurements of the current expansion rate of the universe are quite incompatible. Notably the measurements that you use the cosmic microwave background, and measurements that you use the objects that are very close to us. Okay. And so this is a more, let's say, recent motivation to keep tracking modifications of lambda CDM. But there are many, many modifications to lambda CDM model, okay? Most of them are based in trying to modify the theory of gravity, okay? But there are many ways in which you can modify general relativity. I have worked with these kinds of models called the Horndesk theories. Okay, in this figure they seem a very particular option, but in fact they are quite general family of gravity theories, and they have as particular cases other theories that are here. Okay. And basically these are the theories, these are the most general theories in which you keep the field equations, the Einstein equations, second order, but by adding just one extra degree of freedom, a scalar field. A scalar field to describe dark energy. Okay. A general feature of these theories and of modified gravity theories is that they often introduce a time-dependent Newton's constant, effective Newton's constant, okay, that varies through cosmic time. So in different cosmological epochs, it has a different value. But of course, all these theories, they change all sorts of cosmological observations, and they have to be tested. And so one common way of trying to detect these deviations of general relativity in the large-scale structure is by measuring what is called the gravitational slip. So basically, in the large scales, there are two gravitational potentials in these theories. One that is responsible for making the matter cluster and form structure, and another one that is responsible for bending the light rays. And this does not happen in general relativity at late times, but happens in general in all these modified gravity theories. So by measuring the difference between these two potentials, you detect, in a model-independent way, deviations from general relativity. And why am I talking about this? Is because whenever you have these deviations in these observable, you also have changes in the propagation of gravitational waves. These observables, they are connected somehow. So let's talk a bit about gravitational waves. So gravitational waves, as you all might know, are these very, very small space-time distortions that travel like waves and that are generated by different kinds of sources, but very importantly, these coalescing binary systems, like binary black holes or binary neutron stars. When they're generated by binary systems, the waveform that we detect here is divided in these three phases in spiral, when the objects are slowly approaching each other, and then there is the merger, and then there is ring down oscillations. But the shape of this wave depends on several properties of these sources, like the masses of the black holes, their spins, their position in the sky relative to the detector, their distance, and so on. So, yeah. For the purpose of doing cosmology with these signals, what is important to know is how all these quantities are distributed. So it's very important for cosmology to know what is the probability distribution for the masses of the black holes, the black hole mass function, how this population is distributed across different redshifts, and these things that, from the experimental point of view, are very unknown today, okay, with current detectors, current gravitational wave detectors. And so the current gravitational wave detectors are the LIGO and Virgo, basically, that are operating. I show here in this figure their sensitivity curves, the sensitivity curve of LIGO. But there are next generation detectors that are being planned, such as the Einstein Telescope and the Cosmic Explorer, that are the European and the American projects. Brazil had just entered a few weeks ago the Einstein Telescope. We have these BETS, is the Brazilian Einstein Telescope Studies. There is a research unit in the Einstein Telescope. And there are people doing cosmology, but also astrophysics in this group. Basically, these next generation interferometers, they will improve the sensitivity of LIGO, as you can see here, and they will also allow us to see things in a wider frequency band. Okay? So basically, with these detectors, you see all the binary black holes with low mass. Okay? And there is also the LISA project, that is a space-based interferometer as well, that is not in this figure, but it would be here in the millihertz band. And also these pulsar timing arrays that are a different technique of detecting gravitational waves, and that are sensitive in the nanohertz band. We will talk a bit about this. But before we continue, let's take a moment to just look briefly about what happens with gravitational waves when we are working beyond standard model. Okay, so in general relativity, gravitational waves, they travel at the speed of light, and they evolve like radiation, which means that their amplitude is inversely proportional to their distance. Okay. In general relativity, this distance is just a luminosity distance. That one I showed early, that you can measure using supernovae, right? But when you go to modified gravity in general, these waves propagate differently, and they continue following a wave-like equation. That is what is written here, with a damping term, that is the second term, that already exists because of the expansion of the universe, so already exists in general relativity, but it is modified by the presence of this function alpha m, which is basically the fact that you have a running Newton's constant in these theories. So it damps even more the waves. Okay, and you also can have a excess of speed, or a lack of speed of propagation. Okay, it can be different of the speed of light. So the fact that you have an extra damping in this equation makes you attribute to the same source a different distance. So you see it farther away if you're in modified gravity as compared to general relativity. So these allow you to define a new cosmological distance that is called the gravitational wave distance, that is not anymore the same distance that you would measure with a supernovae, not the luminosity distance anymore. But there is this extra factor here correcting it, that is sometimes called psi in the literature, but basically is tracking this evolution of the Newton's constant. Okay, so now let's enter the main thing, which are, we know that gravitational waves, they will be seen with different distances depending on the model. They are standard sirens, so we can measure distance with them. So how we can do cosmology with this? There are different ways of doing this. I will not cover all these methods, but I will start talking about the stochastic gravitational wave background, and then we talk about these dark sirens, which are these events that you only detect the gravitational wave, no electromagnetic counterparts. And then we talk about the bright sirens that you detect gravitational wave and all sorts of electromagnetic counterparts. So the stochastic background. So the stochastic gravitational wave background is this background of all the gravitational waves that you cannot see individually. So in fact, it can be generated also by cosmological effects like phase transitions in the early universe and so on, but here I will focus on the astrophysical background. So these are basically very gravitational waves that get together. Okay, so it's a very weak signal that you don't detect with a single detector, but it creates correlations between the noise of two different detectors, because it's hidden there in the noise. So it has been shown that you can actually measure the stochastic background if you do the correlation between the signals of two detectors. Okay, but this is a very weak thing. It's proportional to the square of the amplitude of the gravitational wave, and it's directly related to the energy density that the gravitational waves are bringing. So if you can model this energy density in terms of what is the population of binaries that are generating these gravitational waves, or what is this cosmological model, underlying cosmological model, and so on, you can have a model that you can test by measuring this stochastic background. I have worked a bit with stochastic background with the people in UFRJ. We were asking which kinds of changes in the observables you can have if you are in modified gravity theories in general. Okay, and we concluded that the energy density that is being brought by this signal will not be changed if you are in modified gravity theories. This is a bit invariant quantity. And, but the correlation between the signals of two detectors, this will be sensitive to this time variation of the Newton's constant. So in the future, this signal could also, in principle, be used to track modifications of general relativity. And the stochastic background was actually observed already a few weeks ago, 2 months ago, something like this, you might have heard, by these pulsar timing array techniques. And how does it work? Well, you have a pulsar that is rotating very irregularly, and if you have a gravitational wave, a stochastic background, specifically in between you and the pulsar, this will create time dilation, and we will either enlarge or decrease the period of the pulsar, right? But this is very small. Even if we measure the period of the pulsars with a lot of precision, this is very small. However, if you have an array of pulsars, you can correlate these excess of periods that they have, and you can predict that their correlation depends on their angular separation in the sky, and you can measure this. So that was done. So basically, they measure this nanograv collaboration, also other collaborations of pulsars. They measure this function, this correlation between the time residuals of the pulsars as a function of their angular separation. And they found enough evidence for the stochastic background. So this is the shape that you can predict if the time dilation is being generated by a stochastic gravitational wave background. Okay. And unfortunately, they could not say what was the origin of this background, if it's a cosmological origin, if it's inflation, what it is. But the most, let's say, standard hypothesis is that it's generated by these binaries of supermassive black holes that are in the center of galaxies. But we will not only see stochastic backgrounds, diffuse thing of gravitational waves. We actually detect individual gravitational waves, right? We have detected with the 3 first observational runs of LIGO so far about 100 gravitational waves, individual events. And now there is the 4th observational run going on. And so most of these events, how they are events in which you only detect the gravitational waves. They are generated by binary black holes that you don't see electromagnetic counterparts. And these are called the dark standard sirens. And so the question is, when you see a binary like this, only not with your eyes, but with the gravitational wave detector, can you do cosmology with this, with just this information? So what happens? When you see a binary like this, you can measure with certain uncertainty its distance, this gravitational wave distance that we were discussing about. And you can also have a very poor notion of where it's located in the sky. You can also infer other parameters of the binaries, of course the masses and so on, but let's focus on these two. So what people have thought about was, okay, we cannot compare distance with redshift because we don't have the redshifts. The gravitational waves, they don't give you the information of the redshift of the source. So we cannot reconstruct the expansion history of the universe just with the distance. But what people have been thinking about is to cross-correlate this with galaxy catalogs. So if you have a galaxy catalog, you can, and if you could identify what is the host galaxy of that binary, you could have a measurement of the redshift. The problem is that we have such a poor notion of where the binary is located in the sky. There are many galaxies that could be the host galaxy. Okay, so here is the challenge. You have to be able to model and to attribute a probability for each of the possible galaxies of being the true host based on the galaxy properties. So that's the method basically. And so basically, as I was saying, you have a large uncertainty in the sky position. Here I'm showing a plot of LIGO, of some of the LIGO events, so for you to have an idea. When you have more than one detector operating, you have quite good improvement in this measurement. But still you have a sort of multimodal probability distribution for the redshift. So that's one of the challenges. The other challenge is that our galaxy catalogs, the galaxy catalogs that exist so far, and the ones in the future as well, they are not complete. You don't see all the galaxies up to a certain distance. They are magnitude limited. Okay, so what if the true host galaxy of that event is not in your catalog? So when that's the case, what you can do is to have a certain modeling for how the population of binary black holes is distributed across redshifts. So this, of course, will grow with the volume, and here we'll enter the cosmology, but it will also depend on this merger rate, so the amount of mergers that occur per redshift per volume per year, right? And this merger rate, here is the last measurement of the LIGO. It's poorly constrained so far. Okay, but you can model it and you can kind of marginalize over the parameters of this merger rate. And even if it's poorly constrained, people have shown that the method actually works because you have 100 dark sirens so far and just one bright siren. So you gain a lot in the statistics. Okay, so here is basically this plot on the left. You're seeing the distribution for the Hubble parameter from individual dark siren events. So you know basically nothing. But when you put them all together, you have some constraint. Okay. For now, this is not competitive with what you have from the cosmic microwave background, but here you have just 50 dark sirens, and you see maybe hundreds of thousands of dark sirens with these next generation detectors. In this plot on the right, I'm showing you just a comparison of all the dark sirens that we saw so far in black and the single bright siren that we saw so far, the constraints that they give in the Hubble constant. And they are quite competitive. Both very weak until now. Okay, so let's talk about the bright standard sirens. So the bright standard sirens are the multi-messenger events that maybe are more interesting for you. So they are basically generated by mainly binary neutron stars that we know. Just one event of this kind was detected in 2017, the GW170817. Here you have a picture of the detection of the LIGO detection, also Fermi, the gamma ray. And basically, this was a binary neutron star that was very close to us, only 40 megaparsec from us. And so that was a very special event. And for instance, for this event, you could measure the time delay, the difference in the times of arrival of the gamma rays and of the gravitons. And this gives you a very precise measurement of the speed of propagation of gravitational waves. Okay, very precise, up to the 10 to the minus 15. Okay, so basically, it has to be the speed of light. And this had dramatic consequences for modified gravity theories, because there is a whole families of modified gravity theories that predict different speed of propagation for the gravitational waves. And so this killed, within the Horndeski theories especially, this killed a lot of theories. So showing how important and powerful are the bright sirens for modified gravity. But that's not the only thing you can do with bright sirens. The maybe obvious thing that you might thinking is that, well, now that you have electromagnetic signals, you can measure the redshift. At least part of these events, you can measure the redshifts of the source, and you have an independent measurement of the distance as well. So now you can do the sort of Hubble diagram that you do with supernovas, and that you obtain a very good measurement of the Hubble constant that is in tension with the CMB experiment. You can also do this with the standard sirens, the bright sirens. So basically, this relation will now, if you are in beyond standard models, this relation will not only depend on the expansion history of the universe, but because the distance is different, it will also track the variation of the Newton's constant, so you have an additional effect of modified gravity. I have worked a bit with that as well, doing some forecasts for the Einstein Telescope. And so the Einstein Telescope, we will see, let's say, order hundreds of events with gravitational waves and simultaneous detections of short gamma ray bursts, for instance. And for these kinds of events, you have a more precise measurement of the distance, because you also saw the gamma ray burst, and it helps you break in the generalities between parameters, so you have more precise measurement of the distance, and you can do this test. So basically, if you fix the cosmology, if you fix the cosmological parameters that are there in the standard model, so the Hubble constant, the amount of matter in the universe, etc., we showed that you can constrain very generic deviations of general relativity that are called f of r theories up to the percent level with this test, only with this kind of events that, as a reminder, is less than 1% of the events that we see with the Einstein Telescope. Another thing that we looked at is how this compares to measurements of large-scale structure, more standard tests of gravity that we already do. So as I mentioned before, there is this observable, the gravitational slip, that measures the difference between the two gravitational potentials that exist in the large scales, the one that bends the light rays and the one that controls the clustering of matter. And since these two observables, the gravitational slip and the gravitational waves, they are generated by the same terms, let's say, the same effects of these models, you can compare them easily without having to specify a single model. But you can deal with generic families at the same time, and that's very useful when you have a lot of models, right? So basically, what we concluded is that when the cosmological parameters are fixed, the bright standard sirens and measurements of the gravitational slip are quite comparable. They will be quite comparable in constraining the evolution of this effective Newton's constant, that is what is plotted here. Sorry, this is the error in this parameter tracking the evolution of the effective Newton's constant. But this depends on the exact amount of bright sirens that we will see, on the exact precision that we will measure the gravitational slip with future surveys, and so on. Another thing you can do is to combine these forecasts with other kinds of cosmological observations. So for instance, here I'm showing a combination of these constraints from bright sirens, the future constraint, with current CMB data from the Planck satellite. And you see that it will improve both the measurement of these, the detection of these beyond standard models, and also the measurement of the Hubble constant. However, the test with bright standard sirens alone is very degenerate. So basically, only with this distance-redshift relation with bright sirens, you cannot distinguish much if you are in a model with a bit more matter in the universe or with a bit of modified gravity. Alone, it's not very good for distinguishing scenarios like this. But when combined, yes, because then you break the genericis with other observables. So another thing that actually I'm working now is to combine these bright science tests with supernova observations, which is kind of obvious if you think, because if you are interested in tracking how these effective Newton's constant can be measured throughout several redshifts, you can just compare directly measurements of luminosity distance and of gravitational wave distance, right? So that's what we are doing right now. So basically here we have different forecasts for both supernova observations with the Roman and with LSST, and also different scenarios in which you observe gravitational waves and also a kilonova, and gravitational waves and also a gamma ray burst. And then what we showed is that the relative error in this evolution of the Newton's constant will be quite well measured over a wide range of redshifts. Basically, we measure this constant, this quantity today until now. So in the future, you'll be able to measure it even with less than % accuracy up to redshift 0.5, and then with a bit higher errors up to redshift 1. The last kind of test with bright science that I wanted to mention is based on the fact that they are not only distance indicators in the sense that you can measure distance, and if you also can measure the redshift, you can track the expansion history of the universe. They are also tracers of the matter fields. So the inhomogeneities in their distributions are also tracking the inhomogeneities in the distribution of the dark matter, like the galaxies do. And so, for example, you can use bright sirens to measure the peculiar velocities of the host galaxies. Because if you see a bright siren, you know both the redshift and the distance. And if you can identify their host galaxy, you can see you can measure the redshift of the host galaxy, and you can subtract the amount of this redshift that due to the cosmological redshift because of the distance. And then you can measure this excess of redshift, which is basically the peculiar velocity, the velocity of the galaxy with respect to the Hubble flow. And this field of peculiar velocities of galaxies is very important because if you have the field of peculiar velocities of galaxies, also the field of galaxies itself, the density of galaxies, and also the density of the binary black holes, you can do cross correlations between all these fields and break a lot of the genericies that you have in these distributions. Because you have, for example, bias relative to from the galaxy to the dark matter field and these kind of things. And we can use these cross correlations to measure the growth of structures. So it's a component of the cosmological model that is not only in the background, not only expansion of a homogeneous universe, but also the growth of the structures, so about the inhomogeneities in the universe. And all of these methods, I mean, they can be applied also with supernovae, right? Supernovae are very similar to bright science in this sense, with the exception that you measure a different distance, so we will not track this evolution of the Newton's constant with supernovae. So it's not very sure which kind of which of these probes will provide better, more precise measurements of Hubble constant, for instance. But they have some differences. For instance, the supernovae, they have to be calibrated. You need Cepheids or some other distance indicator to calibrate, because the intensity of the supernova, it's not directly the distance, it's just proportional to the distance. So you need some calibration. And this calibration puts some lower bounds in the errors that you have in distance measurements in supernovae. This does not happen with bright sirens, because you measure directly their distance, you don't need to calibrate them. So as long as you have better and better interferometers, you don't have, in principle, a limit for these measurements. So basically, that's it. How cosmology that can be done using gravity you can use to measure distances in the universe as the same as supernovas, and they are also tracers of the matter field. So they track also the distribution, the inhomogeneities in the distributions of the matter field. And beyond lambda CDM models, modified gravity models, they are very important because they track specific features of these models. Not like the cosmic microwave background or the galaxy distribution that are sensitive to all the details of these models. No, they basically track this evolution of the Newton's constant. So they can be used to break degeneracies when compared to other cosmological observations. And what I think it's very important from now on in this field, in this topic, is to basically explore to the maximum the combinations of different types of gravitational wave observations with other cosmological probes because of this power to break degeneracies. And also to try to build more model-independent tests of gravity with using gravitational waves, and especially the dark sidings. Because now this dark siding technique, for you to do that, you need a lot of modeling, both on the astrophysics and also in the cosmology part, you have to fix the model. So it would be very interesting to build more model-independent tests with these kinds of observations. And that's it. Thank you for your time.
Thank you very much, Isabella, for this great talk. So let's start with the questions here.
Thank you, Isabella, for the clear talk. Could you explain a little bit more about this? This is a new thing for me, this gravitational sleep, and if it has some impact on the analysis of gravitational lenses.
Yeah, so the gravitational lensing, sorry, let me just put in the figure. Here. So the gravitational lensing is actually one of the kinds of observations that you use to measure the gravitational sleep. So in a galaxy survey, you have there you measure the lensing, the shear of the galaxies, and you also measure the distribution of the density of the galaxies itself. By combining these two things is that you obtain the gravitational sleep. So it's a measurement of how differently the photons feel the gravitational field with respect to massive particles, basically. So I don't know if I answered your question.
Yes.
So basically this is a test that people do in galaxy surveys. Normally when they look for beyond lambda CDM models, this is one of the things that they look, is the gravitational sleep.
Thank you for your talk. It was very nice. Following this question on the gravitational slip, is it like, you say it was model independent, the measuring the slip?
Yeah, you can show that you can measure the gravitational slip with very few assumptions. So if you want, there is a reference, maybe I didn't put here, but basically is a quite direct measurement of the data. You don't have to assume that you are in the f of r theory with a certain Lagrangian, certain parameter values to be able to measure it, you see. So if you have a modified gravity model in general, you have this eta gravitational slip different from 1. So if you measure it different from 1, you know that you are not in lambda CDM.
I see. Okay, just another question. You say measuring gravitational waves gives us model-independent distance, but it was weird to me because I think you showed the gravitational wave distance as like a function of the evolution of Newton's constant.
Yes.
And isn't that dependent on the model which you assume? How the
Yeah, you're right. In a given model, you have a certain function that is this time-dependent Newton's constant, and this will give you a certain function for the gravitational wave distance.
Right.
The thing is that if you can measure the gravitational wave distance in different redshifts and compare it to the luminosity distance in different redshifts, you can measure this Newton's constant at that redshift. You understand? So you don't have to specify a model to be able to do this test.
Okay.
You can see if it's a constant or if it's not a constant from the data directly.
Okay, I understand. Just to finish it off, these models which assume time-dependent Newton's constant, they assume things like this Newton's constant increase or decrease over time generally?
It's a good question. Wait. So the gravitational wave distance is smaller than the luminosity distance. and it is, what is it? So this is smaller than this, so this is smaller than this. So it increases with time. So it increased from the early universe to now.
Okay.
Yep.
Interesting. Thank you.
Sorry.
Hi. Thank you very much for your talk. And my question is, can you detect cosmic strings with gravitational waves?
Yeah, so I know that cosmic strings, they generate this stochastic background of gravitational waves as well. And it's one of the candidates for stochastic background searches. But so far, we could not say that there were, the one that was detected, we could not say that it was from cosmic strings. But it was not ruled out as well. So in principle, yeah. In principle, with future detectors, with pulsar timing arrays and also with LISA, you will be more sensitive to these stochastic backgrounds. So maybe they can also see the one from cosmic strings if it exists.
Thank you very much.
Thank you, Isa, for your presentation. Regarding this alpha parameter and the speed of propagation, when you're showing the results from the bright siren, the GW17 something, that constraining alpha less than 10 to minus 15 is just by calculating the time interval between the two two messengers.
Yes, this was a measurement of this alpha t, not of this alpha m.
This alpha t. Yeah, exactly.
Yeah, exactly. This was just by comparing the time of arrivals of the two kinds of signals. You have to consider that they travel a long distance. So if there was a small change in the speed, in the relative speed, you would be sensitive to this. It would cause a big time difference of arrival.
Yeah. Okay. And is there any impact on the theory of the Horn-Deskis
Yes.
for gravity?
Yeah. So I have one slide here. Wait, is that in the end? No. Oh wait, sorry, I went in the wrong direction. Yeah, so basically I didn't want to show a big equation, but basically this is Lagrangian of these Horn-Deskis theories. So they depend on these four arbitrary functions of the scalar field, its kinetic energy, and so on. And with this measurement of the gravitational wave speed, you basically ruled out or highly disfavored all these last term here, and also this second term here on the L4. Okay, so all of these was thrown away, kind of, because of these measurements. So that was the best constraint in these theories that are there since the 70s. Okay, there are some arguments against this, but putting them aside, it was a very strong constraint in these theories.
Okay, thank you.
Questions?
Thank you for the excellent talk. I was wondering, because when you showed the data for the supernovae and the gravitational waves, there are two different ones, the realistic and the optimistic ones. So can you comment on the difference between them?
Yeah, sure. So in the case of the kilonova events, so the events that are closer, we expect to see a kilonova explosion, right? This part of them. And so optimistic and realistic is related to the amount of time that the LSST would dedicate to do the follow-up. So I think the values are 10% of the time and 50% of the time. Okay, in this case. And for the events with short gamma ray bursts that are fewer, but you can see farther away, optimistic and realistic was, let me remember with the gamma ray burst. I think it was in the ability of measuring the redshift for a given power of on the sky localization. So one assumes that you can measure the redshift always, I think, and the other one only if you measured it with less than, I think, 5 degrees or something. So,
Okay,
yeah.
thank you very much.
Welcome.
Okay, I have a question myself. Which kind of instrument would have the Einstein Telescope on board?
So the Einstein Telescope would be an interferometer in Earth, like LIGO, but underground. So just like LIGO, but underground, and also with bigger arms. I think 10 times or 5 times larger than the arms of LIGO. And it will have probably a triangular shape, so that you can have more than one interferometer in the same instrument. So it improves also the sensitivity.
So and for detecting the, let's say you would like to see the gamma rays counterparts.
Yeah.
Are you planning to couple with which other instruments?
Yeah, so I know there are groups working doing the synergies with gamma ray observatories.
Yeah.
What I've seen, so the forecast that I'm using here, for example, they are using this Theseus. I don't know if you, maybe I guess you know, this project for the future, to detect gamma ray bursts, both short gamma ray bursts and also long gamma ray bursts.
I see.
And that was what I used.
Okay.
Because it's more, because the Einstein Telescope is for 10 years, 20 years from now.
Yes, I see.
So you have to compare with future
instruments.
Yeah.
I see. Okay. Questions? Yeah.
A very basic question. When gravitational wave intercepts matter, or when matter intercepts gravitational wave, part of the energy is dissipated by the matter?
Yeah, so gravitational waves, they interact very weakly with matter. But there are some effects. There is gravitational lensing, for instance, weak gravitational lensing, like there is with photons, there is with gravitons as well.
But part of the energy is deposited into the matter, like in electromagnetic waves?
I guess so, but I cannot tell you how much.
By frictional effects
Yeah.
Converts some of the waves in heat of the matter. Can it happen with gravitational wave?
I don't know if it can happen in a non-negligible way. From what I know, they interact very weakly, like neutrinos, like they go over it, because they themselves are very small. Their amplitudes tend to the minus 22 already. So yeah, I cannot give you a number of, but in principle, there is some interaction.
More questions? Yes? Great.
Okay, thank you, Isabella, for a great talk. I just had a brief question about using the merger rate redshift evolution from LIGO to try and do cosmological tests. If you can, yes, this one. So the idea is that you're using that to try to constrain the redshift of the BH-BH merger observations because you don't have them from the galaxy catalog. But then in this case, I think that the merger rate that LIGO has, the redshift evolution itself, they need to assume a cosmological model to estimate the redshift from the signal. So there's another source of degeneracy here, which there are a lot of them. And so I was wondering if anyone has maybe tried to estimate how much variation we could get in that curve that you show here from different
from cosmology.
From different cosmology or modified gravity, maybe.
I think the highest, the biggest uncertainties, they come from the astrophysics in this case, not from the cosmology.
For now, we wouldn't be able to detect that.
Because from the cosmology side, basically, you have to set the H0 to do this translation. But I don't think in the end it depends very much on the value of H0 that you used. Whereas if you look at the error bars,
they're very broad. So even with, if we get before 2030 the Voyager update to LIGO, and observe the mergers at higher redshift, we still would get it very broad.
I think with Voyager it will still be bad, but with third generation, no.
Okay.
Yeah, because with third generation you also see farther away, so you will be able to see if there is any feature, if there is a peak, because we expect that this function there is a peak.
Yes.
And so you'll be able to go deep enough to see if there is a peak and so on.
Okay, thank you.
Okay, so if there is no more questions, let's thank again Isabella for a great talk. And I invite everyone to the coffee break.
Obrigada.
Muito claro.
Ai, que bom.
Pode desligar a...